In this video, we're going to do the free response for Chapter 9 and 10 that's labeled 2009B number 5. And we've actually done this one before, so probably will seem familiar, but it's still good practice. But hopefully you should have been able to do Part B more on your own than the first time we did this problem a couple months back. But I'm going to work it out. So it says a bottle filling machine is set to dispense 12.1 fluid ounces into a juice bottle to ensure that the machine is filling accurately. Every hour, a worker randomly selects 4 bottles filled by the machine during the past hour and measures the contents. If there's convincing evidence that the mean is different from 12.1, or if there's convincing evidence that the standard deviation is greater than 0.05, the machine is shut down for recalibration. It can be assumed that the amount of juice that is dispensed into bottles is normally distributed. During 1 hour, the mean number of fluid ounces of 4 randomly selected bottles is 12.05 and standard deviation is 0.085. And Part A says perform a significance test to determine whether the mean amount of juice dispensed is different than 12.1. Assume conditions are met. Okay, so that was kind of a lot. Let's make sure we understand. So this is saying that the mean is 12.1 and the standard deviation, that's what they want it to be, right? We don't want it to be different than that. That's kind of like your ideal population. We want to know, we're trying to test, is our population mean different than 12.1 or our population standard deviation greater than 0.05. Down here, this is one sample, right? This was the mean of our sample, so that's X bar. It's 12.05. And the standard deviation of our sample is 0.085. Okay, so make sure you use the right notation. And now we're going to perform a significance test to determine whether the mean is different than 12.1. So what we're asking ourselves is, based on this sample result, do we have reason to conclude that our mean is different, the true mean is different than 12.1? Okay, we can see that our sample mean is not 12.1, but is it far enough far enough away, right? It's the idea behind the p-value. It's what's the probability, if it really is 12.1, of getting this sample result. If it's a small chance of getting the sample result, then it's probably not 12.1 and it needs to be recalibrated. So I really want to emphasize, I hope y'all are starting to grasp the idea behind a p-value in these significance tests, because who knows how we're going to ask it on this shortened version. So we're still going to do our normal state plan, do conclude. So our HO is always equal to, what do we set equal to? We want to know, is the true mean, is mu, set it equal to 12.1. That means it's not different than what they want it to be. And that means our alternative, we care, is that true mean just different. So if it's not greater than or less than, but just different, you do just not equal to 12.1, and we can go ahead and it'll give us an alpha, so we'll write down our alpha. Oh, and I almost forgot, one of the most important steps is defining that mu, right? What is mu representing? The true mean, or the population mean. Try to use true or population to make sure you don't mess up. True mean, and then I would just use your sentence. Amount of juice dispensed in, oh wait, I'll just leave it in dispensed. I was going to write in different, that doesn't make sense. Okay, so it's the true mean amount of juice dispensed. Maybe I could even say into all bottles, right? I'm not just talking about the 4, but into all bottles. So now we're ready for plan. So this plan should be pretty short. First we're going to pick our method, which it's just a one mean test, right? So what we call that is a one sample t-test. And then we can just say assume conditions are met because it told us, right? So I'll just put assume conditions are met is what we are told. And so then we can go straight to do. And now I'm going to be pretty explanation-y. I know that's not a word, but I'm going to go really in depth about these numbers because, again, I'm just worried that I don't know how they're going to test it on this new format. Okay, but what you would first do is get your calculator. If you're going to use your calculator, if you're not going to do it by hand, but if you weren't doing it by hand, you would need your test statistic first, so you'd have to use that formula. But you would go to menu, statistics, stats test, and one sample t-test isn't on here, it's just this t-test. That's one sample. And we just have the stats. We don't have all the data for our sample. And what did we set our null equal to? 12.1. Our x bar was 12.05. Standard deviation was 0.085. Our sample size was 4. And we set our alternative to just be not equal to, so we keep that. And we have all this information. So we need to write down all this information, and then let's kind of make sure we understand what each thing is. So we have our t-value equals negative 1.176. Our p-value is 0.324. Our degrees of freedom equal 3. We already wrote down our x bar up here. But you can, I would just be careful, write everything from your calculator again. And our sample standard deviation was 0.085, and our sample size was 4. So also, you write everything down from the calculator, but you also need to draw your distribution. So we draw a normal distribution. Now this is like a standardized version of your sampling distribution that we talked about in chapter 7. So this is like a standardized form of if we took a bunch of sample size of 4 and we got the x bars and we plotted them all, but then we standardize it to make 0 in the middle. So this t-value is like a test statistic for your sample result. So you're going to put that negative 1.176, and then we're going to shade because based on this, right? So you shade in the tail going less than, and then because it's not equal to, it's two-sided, you also have to go to the positive version of your test statistic and shade in that tail. Now those should be equal. I know it doesn't quite look equal. So this is a standardized form of how far does our test statistic fall from our sample value or our population claimed value of 12.1. Okay, so our sample result is about negative or 1.176 standard deviations away from this 12.1 mean. That's what the t-value is. Now our p-value is this area that's shaded. So if you were going to actually find this area by hand, you would get this p-value. And then the degrees of freedom is, we know, is n-1. So that p-value, when you know the interpretation also, is the probability of getting our test statistic or our sample result or something more extreme. That's why you're shading away. If the null is true. So if the null is true, the probability of getting our sample result is 0.324, which is a high probability. That's like 32%. That's not that crazy. So for our conclusion, we say since the p-value is greater than alpha, equaling 0.05, we fail to reject HO and do not have convincing evidence that And now we just put HA in we don't have convincing evidence that HA, and then we'll say that the mean, or I'll say the true mean amount is different, or you could say not equal, different than 12.1. So what does that mean? We don't have convincing evidence that it's different than 12.1, so we're not going to recalibrate the machine yet, right? We're only going to recalibrate if it's not. We have convincing evidence that it is different than 12.1. Okay, so for part B, that one should have been pretty straightforward. Part B says, to determine whether the sample of 4 bottles provides convincing evidence that the standard deviation of the amount of juice dispensed is greater than 0.05 ounces, a simulation study was performed. Right, because we don't, oh, I just realized y'all can't see anything. There you go. Because we don't have a test, we only have tests for proportion and mean. We don't have a test for standard deviation, so they kind of had to makeshift their own version. So it says, in the simulation study, they took 300 samples, each of the same size, 4, and were randomly generated from the normal population with a mean of 12.1 and standard deviation of 0.05. So those are your population values. The sample standard deviation was computed for each of the 300 samples, and they put it on this dot plot. So what they created here was like a sampling distribution. Sampling distribution of what? Not of means, of proportions, but of standard deviation of x. It's a sampling standard distribution of your sample standard deviation of n equals 4. So this is like that distribution we draw where we shade. It's just not standardized. It's not getting 0 in the middle. So it says, using this result, using this sampling distribution they created, explain why you think the sample provides or does not provide evidence that the standard deviation dispensed exceeds 0.05. So you don't have to do a full-on state plan to conclude, but I do kind of want to set up what are we trying to test and think about it that way, and it might help us. So we're trying to decide, is our population standard deviation, which would be this, right? For hypothesis, you always use parameters, population symbols. Is it different or greater than 0.05? So your alternative would be greater than 0.05. We want to know, do we have convincing evidence for this alternative? And you don't really have to go through and do all this stuff, because this isn't wanting a full, it's just saying, do you have convincing evidence for this HA? So how do we know if we have convincing evidence for that HA? Is ultimately you need a p-value. We want, what's the probability of getting our sample result? So what is our sample result? Our sample standard deviation was 0.05? No. Wrong. 0.085, right? That was the population standard deviation. Where? Oh, here. Sorry, I couldn't find it. I circled it, but you couldn't see. Our sample standard deviation was 0.085. So we want to ask ourselves, what's the probability of getting this sample result if the true standard deviation is 0.05? So they made this sampling distribution assuming out of a population where the standard deviation is 0.05. So on this sampling distribution, what's the probability of getting this standard deviation? 0.085 would be like about right here. That is where our sample result falls. And what's the probability of being greater? So you would shade, if you were going to do p-value, you would shade to the right. So we can kind of emulate what is this probability of being greater than 0.085. So our p-value, notice we didn't get our test statistic. I didn't change this to be T or Z. You don't theoretically have to do that if you have the sampling distribution. So how many were greater? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think I counted, right? Yes. So 12 out of the 300 different samples they took had a sample standard deviation greater than ours. So what's the likelihood of getting our sample result or something more extreme? 12 out of 300, which if you change that to a decimal, it's 0.04. So is that a small p-value? Well, normally what? We compare it to alpha being 0.05. So we will say yes, since this p-value is less than alpha, we have convincing evidence. What? That the standard deviation of the juice dispensed exceeds 0.05. Have convincing evidence for this HA. So we'll say, since p-value 0.04, oops, I did parenthesis one side, comma on another side. Guess I'll put parentheses now. Is less than alpha equaling 0.05. Now you can write out the whole sentence, we reject, if that's what you're comfortable with, or you could just really go straight to what they asked, since this is kind of like a makeshift state plan do conclude. I guess I'll write it all out just to make y'all happy. Since the p-value is less than alpha, we reject HO and do have, and now what I would use is this sentence. Convincing evidence my marker's going out that, and now we just write this, the standard deviation, I'm going to abbreviate, of the juice dispensed, if I could spell dispensed, exceeds 0.05 fluid ounces. Okay, so that's perfect timing because my marker's dead. But I hope that makes sense and you really grasp this idea behind the sampling distribution and the p-value and what does that mean, how does our null come into play, and how does that prove the alternative. We will do the other free responses in the next videos.